Morning, guys. Today we are going to take a look at section 5.3, which talks about exponential functions. An exponential function is in this form right here. So f of x equals a to the x power, where a is the base of the exponential. A is going to be a positive real number. It's going to be greater than 0. The domain of an exponential is the set of all real numbers. We can plug anything into these. And what we're plugging things into is this exponent right here. So the x is your exponent. So that's going to keep changing as we put different values into it. Okay? The base, a, is called the growth factor. And that can also change problem to problem. But what that number starts with is going to affect how the graph looks and how the function grows. Okay? So the first thing we want to do is we just want to take a look at a couple exponential functions. First one is just 2 to the x power. We're going to graph it, and we're going to graph it using a t-chart just so we can get an idea of what this thing looks like. Whenever I do a t-chart, I like to plug in like a 0, plug in a 1, a 2, a 3, plug in some positive numbers, maybe plug in some negative numbers so we get an idea of how, excuse me, it should be a 3, of how negative numbers apply to this function. So 0, first off, anything to the 0 power is just 1. So that's where we're going to start. And then if I plug in a 1, well, anything to the first power is just itself. So that's going to be a 2. If I plug in a 2 squared, that's going to be a 4. And if I plug in a 3 right there, 2 to the third power, I'm going to get an 8. Now, it may not look like these are getting huge, but as I keep going, just up a little bit more and up a little bit more, these numbers are going to get big in a hurry. So if I were to plug in a 4, I'd get a 16. If I plugged in a 5, I would get 32. So these are going to go way off my graph really fast. Okay. In fact, this one barely is going to stay on. Now, so what's going to happen with these negatives? What is 2 to the negative first power? Well, a number to a negative power is the same as 1 over that number to that power. Okay, so a negative exponent really means that this is taking place in the denominator of a fraction. So this is 1/2. If I plug in a negative 2 as an exponent, so 2 to the negative second power, again, that's 1 over 2 to the positive second power, or 1/4. And then if I plug in a negative 3, I'll get 1/8. So here's what this graph's doing. Let's start with the positive. So 0, 1, so I've got that. 1, 2, over 1, up 2. Over 2, up 4. But then over 3, I'm up 8. Okay, so this is what the right side's doing. Kind of reminds you of a parabola. But as I go to the left, negative 1, I only go up 1/2. And when I go to negative 2, I only go up 1/4. So what's happening is the graph is coming down, and it's getting closer and closer and closer to the x-axis. So that's like a horizontal asymptote. Okay, I'm not going to hit it. Even if you put in a negative million, you're still not going to have 0. You're going to have something there. It's going to be barely above the x-axis, but it'll be there. Okay, and as I move to the right, going up, 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 okay? Which is what we think of when we think of exponential functions, that they go up really, really fast, okay? So that's an example of an exponential function. Over here, I've got another one. Now this one has a different growth factor. The base is a fraction. So I'm going to put in the same numbers, 0, 1, 2, 3, negative 1, negative 2, negative 3, and we're going to see how this base is affected by these numbers. So we're going to plug in a 0. Well, that's going to stay the same. Well, excuse me. 1/2 to the 0 power is going to be 1. 1/2 to the first power is going to be 1/2. That's what's going to stay the same. 1/2 to the second power, so 1/2 times 1/2, that'd be 1/4. And 1/2 to the third power, so multiply by another 1/2, you're going to get 1/8. Okay, which looks very familiar to the numbers that we had over here when we were plugging in the negatives. If I take 1/2 to the negative first, so again, what this is doing, this negative exponent, it's going to do the reciprocal of this number right here. So when I take it to the negative first, I'm actually going to get a 2. And when I take 1/2 to the negative second, well, it's going to flip it, and I'm going to get a 4. Okay, it's going to take 1/2 times 1/2, which is 1/4, but then it's going to flip it. That's what that negative is going to do. Okay, and then I'm going to get an 8. So again, you see these numbers over here, but they're in different spots. So I've got 0, 1, that's the same. I've got over 1 up a half, and then a quarter, and then an 8. So this one's going down as I go to the right. And then as I go to the left, it's going to be going up. So I'm just going to go -1, 2, -2, 4, and then up to 8. Okay? And that's also an exponential function. Now, this goes forever this way, forever that way. All right. This is an example of what's called exponential growth. Things are getting bigger as you move from left to right. It's growing. Whereas this is exponential decay. Where as time goes by, it's getting smaller and smaller and smaller, and it's getting small in a hurry. Okay, so this is growth, and we have decay. A lot of the properties of these two are very similar. Okay, so like the domain is all real numbers. You can plug anything in. The range for both of these would be all the y values greater than 0. Y greater than 0. We're not going to hit 0. The y-intercept on both of these is 0, 1. Okay, so again, notice 0, 1 on both of them. There's no x-intercept because we don't hit the x-axis. Why? Because the x-axis is a horizontal asymptote. Okay, now f of x equals a to the x power if a is greater than 1. So that's this situation. So our base is bigger than 1. This is an increasing function. As we move from left to right, it's always going up. Always. Whereas if our base, it's still positive. Notice the base was not negative. The base is a fraction. If your base is between 0 and 1, so if it's a fraction, it will be a decreasing function and will always be going down as you move from left to right. And the graph will always contain the same points. If we write it generically using these bases of A, then the same 3 points are going to be on every single parent graph. Okay, you're always going to have 0, 1. You're always going to have 1 and then the base. Okay, because anything to the first power just stays the same. So when my base was a 2, I had the point 1, 2. When my base was 1/2, I had the point 1, 1/2. But that is the base. That's going to be important to help us graph these. Okay, and then we're always going to have -1 and then the reciprocal of the base. If the base is a 2, it'll be 1/2. If the base is a fraction, it's going to be the reciprocal of that. So it'll be a whole number. Okay, so those are just a couple graphs: exponential growth, exponential decay, and then some properties you can pick up by looking at those. Now, if you look at your second page, okay, so graphing an exponential using transformation. So this is a graph 2 to the x plus 1 power plus 3. Okay, and we're going to graph this. Now, first off, list the 3 points you would use to graph the parent graph. Those are those 3 points I just mentioned, where all we're doing is we're looking at the base. Okay, so don't look at these things yet. We're going to graph 0, 1. We're going to graph 1 and then the base, and we're going to graph -1 and then the reciprocal of the base. Those 3 points. And for these, I actually graph those parent graphs, those parent points. Okay, 0, 1, over 1 up 2, and then -1/2. That's our starting points. You can connect them if you want. You don't have to. If you do connect them, I would connect them with a dotted line, because this is not our graph. These are some points that are going to get moved once we start graphing. And here's how we're going to move them. That's what these numbers are. Okay, so remember, anything that's connected to your x is going to affect your graph horizontally, and it's the opposite of how you think. So that little +1 right there is going to make us go left 1, and then the +3 is going to make us go up 3. So I'm going to take each of these points and I'm going to do that. Okay, I'm going to go left 1, and then I'm going to go up. So remember, look at our y value. We're up a half. So I'm going to go up left 1, and then I'm going to go up 3. So I'm going to go up 1. That's still going to put me halfway in between. I'm going to go up again, and I'm going to go up again. That's where I'm going to end up. This point is a little more obvious because you're right here at an intersection. You can go left 1, you're going to go 1, 2, 3. And then this point is going to go left 1, and then 1, 2, 3. Our horizontal asymptote, which was the x-axis, is now going to be up 3 as well. And that's what our graph is going to follow. And it's going to look like that. Okay, so that's our graph. That's our horizontal asymptote. The directions also ask us to find the domain and the range. Well, your domain is all real numbers. And the range, because everything's shifted up, is now all the y values greater than 3. Okay? So that's how to graph an exponential using transformations. Now, there is one number that you'll see a lot when you start doing exponential functions. It's called e. It's the number e. You'll see this on your calculator. You have an e button. It usually says e to the x power on your calculator. E is an irrational number. It's like pi. It's one of those decimals that goes forever and ever and ever. It is a number that occurs in nature. A lot of times it's called the natural number. And I'm going to show you some examples here in a second that involve e. But e is approximately 2.7, and that's our base. And our base is bigger than 1, so this is a growth function. And this is an example of the parent graph, e to the x power, where you've got 0, 1, you've got 1e, so this is about 2.7. And then you've got negative 1, 1 over e. 1 over e, if you do that in your calculator, you'll get about 0.37. So this is a little bit over 2.5 when you graph it, and this is a little bit under a half when we graph them. So if I was going to graph this graph, but using transformations, like in this example right here, I would start with these points. I would start with 0, 1, 1, e, which is about 2.7, and then negative 1, 1 over e, which is about 0.37. So these are my starting points. Okay, now all of these are going to get transformed. Let's see, the minus 2 is going to make us go right 2. And this negative is going to be a vertical flip. Okay, so like this point right here, 0, 1. 0, 1 would normally be right here. Okay, 1, 2.7. Now this is going to go off the board. 1, 2, and then about 2.7. And then negative 1.37. So here's my starting graph, which is what this one looks like. Okay, and then I have to move. I need to move each of these right 2. So I'm going to go right 2, and then I'm going to flip it. So instead of being up 0.37, I'm going to be down about 0.37. The next one, 0, 1, I'm going to move that right 2, and then instead of being 1 above, I should be 1 below. And then this one, where I went over 1, up 2.7, again, I need to shift it over 2, and then I need to flip it. So instead of being above by 2.7, I'm 1, 2.7 down. Okay, so that is what our graph is going to look like. The domain would be all real numbers. The range, okay, so again, this y equals 0 is still a horizontal asymptote, but we're approaching it from underneath. So it's y less than 0. That's our range. All the y's less than 0. All right, so lastly, I want to look at a couple like real world problems that involve exponential functions. The first, money. You put money in the bank and you earn interest, and that ends up being an exponential function. So this is the amount, or this is you put money in the bank. This is also you borrowing money from the bank, and then you have to pay interest. But A is the future amount. So P is principal. This is how much money you're starting with. You're putting $1,000 in the bank, or you're borrowing $10,000 from the bank. And then this A, that's the amount that you're actually going to end up paying in the end, or how much you're going to end up having in the bank after the interest is calculated. 1 plus R. R is the interest rate as a decimal. It will often be given to you as a percentage, and you'll have to change it to a decimal. N is the number of times that per year that they are going to compound your interest. And what that means is they're going to calculate your interest, they're going to give it to you. Then when they calculate your interest the next time, you're going to be earning interest on that interest. Okay, so you have $100, you earn $1 of interest, and so the next time they calculate it, they're going to be calculating it on $101. So you're earning interest on that interest that you've already made, because that's now your money, if you think of putting it in the bank. Okay, so the N is the number of times they're going to compound it per year. And then there's an exponent here. The exponent says NT. So again, it's that same N times the number of years that you've got your money in the bank, or you're taking out this loan. Okay? So N could be a lot of different things. So if they're compounding annually, so only at the end of the year they're going to compound it, and then they're not going to do it again for another year. So that would be once per year. So that would be your N. Your N would be 1. Semi-annually, every 6 months, so that's twice per year. Quarterly, every 4 times per year, so every 3 months. Okay, monthly, so the N would be 12. Weekly, it'd be 52, so once a week. And then daily means 365 times per year. So at the end of every day, they're gonna calculate your interest, they're gonna give it to you. Eventually, you're gonna approach what's called continuous compound. So continuous compound is like instantaneous. Like every second, they're calculating it, giving to you, calculating it, giving to you. And we get this formula right here. I call it the PERT formula because it's P, again, the principal, and then it's E, that natural number, which is what this right here is getting closer and closer to. Okay, so this is going to end up, if you keep calculating this, you're going to get this base that's like 2.718. It's just this natural number. Okay, it occurs in nature, and in this case, it's happening with this money. And then the exponent is RT. So R is that rate, and T again is the number of time, is the time, the amount of years. Okay, so notice this is NT, this is RT. So try to keep those straight. Okay. So, for example, a credit union pays interest of 4%, so that's going to be 0.04 when we plug it into the formula. Compounded quarterly, so our N is going to be 4 times per year on a certain savings plan. If $2,000 is deposited in such a plan, so that's our principal, that's our starting money. How much is in the account, so what is our future amount of money after 5 years? So, the future amount is going to be 2,000, 1 plus R, which is 0.04, over N, which is 4, and then it's to the 4 times 5 power, okay, NT. And you can write that, you can write 4 times 5. For this one, I would probably just do the 4 times 5 in your head and put 20 there, and that's going to make it easier to plug into your calculator. Now, all of this can be plugged into your calculator at once. Some of you may be a little apprehensive about doing that. You got to be careful with your parentheses and things like that. But if you do, I mean, it's just 2,000 parentheses, and then it's 1 plus 0.04 divided by 4, then close the parentheses, and then it's to the, so there's my little exponent button, to the 20th power, and that's it. So 2,000, so my future amount after 5 years will be $2,440 And whenever you're talking about money, go ahead and just round to 2 decimals. So 38 cents. Okay? And if you wanted to do this in parts, you could start inside the parentheses. You could do 0.04 divided by 4. So do the order of operations, do the division, add 1 to that. Take that answer to the 20th power. Most of you may know you have it's called an answer button right there. And it'll record, like kind of memorize the last answer you had. So if you did 0.04 divided by 4 plus 1 equals, okay, and if I wanted to take that to the 20th power, I could just hit second. Well, this one I wouldn't even need that. Answer to the 20th, and it'll keep track of that for you. And then I would multiply that number times the 2,000 that was out there. Okay? All right. Look at the next one. What is the future amount if 2,000 is deposited into an account that pays 4% compounded continuously? So I'm using this formula for 5 years. So what is the future amount when 2,000 e to the 0.04 times 5? Now, when I go to plug this into my calculator, I'm going to do 2,000, and then you could do times, and then E. My E button is right here. It's above the natural log button, LN. That's something we're going to talk about later as well. Okay, and that's the E, so I'm going to hit second E, and then notice my calculator automatically is asking me what exponent do you want to take this to. Okay, so every time you have E, it's going to be E to some power, and your calculator knows that. And so now I can put in the 0.04 times 5, close parentheses. So this is all connected inside of parentheses, so the calculator is going to do this first. It's going to take E to that power, and then it's going to multiply it times the 2,000. And I'm going to get a future amount of $2,442. Make that an equals. And we'll say 81 cents. Okay? So not a big difference after 5 years between compounding quarterly and compounding continuously, but this is continuous, and that is using just the normal compound interest formula. The last example here says how much principal is needed to get $1,000. So if I want to end up with $1,000, how much money do I need to start with? Okay, after 5 years at 6% interest compounded continuously. So it's going to be E to the 0.06 times 5. Okay, so this would be 1,000 equals P, and then go ahead and simplify this. Like, figure out what this number is. It is clear E to the 0.06 times 5. So I get this 1.35, this crazy decimal here. So 1.349858808. Okay, you may not want to write all that down, but look at our next step. Our next step, since this is multiplying P, would be to take 1,000 and divide it by this. This is where that answer button is going to come in handy. So I don't have to type in all these decimals. I'm just going to take 1,000 and divide it by, I'm going to hit second answer, and it's going to memorize that decimal for me so I don't have to, and I'm going to get the principal of 740. We'll say 82. Okay, so that's how much you need to start with if you want to have $1,000 in 5 years. You got to start with 740. Okay, so these are all examples of what is called exponential growth. The numbers are getting bigger as time goes by. You can also have what is called decay. This is a growth and decay formula right here. So in nature, you've got bacteria that's growing. You've got some kind of radioactive material that has like a half-life of, it's like decaying as time goes by and kind of shrinking. So that's what this formula is. Now, honestly, it's the exact same formula as the PERT formula. This is the amount of stuff you're starting with. So it's not principal, it's not money, it's stuff. It's bacteria, it's insects, it's something. It's some amount that you're starting with. And then it's e to the kt power. So instead of r, which is interest rate, and is usually given to us as a percentage, and then we turn it into a decimal, this k is called the growth rate. And that k can be negative if we have a decay situation, or it could be positive if we have growth. We don't write it as a percentage. It's always just a decimal. And like I said, it can be negative, whereas interest rates can't ever be negative. So your rate with money is always going to be positive. This is a slightly different situation, okay? But it's actually the same formula, just with different variables plugged in. It's written using function notation, a of t, so instead of like f of x, it's a of t, where a is the future amount we're going to have at some time, and t is the amount of time. That time could be anything. It could be days, hours, years, and they'll tell us that in the problem, what it is. Okay, so for example, if you look right here, I've got this bacterial growth. A colony of bacteria grows according to the function, and then, so the amount I have after a certain amount of time, n of t, equals 90 e to the 0.05 t, where n is measured in grams. So you have a certain amount of grams of this bacteria, and they're measuring it in days. So what is the initial amount? Well, that's what the 90 is in the formula. So we're starting with 90 grams of this stuff, this bacteria. Okay, what is the growth rate? Well, that's the 0.05 right there, and we want to leave it k equals 0.05. Don't write it as a 5%. Okay, 0.05. What is the population after 30 days? Well, so that's our t. So the number we have after 30, that's what we're plugging into it, so I'm writing it as a function, is 90 e to the 0.05 times 30. And again, you're just going to plug that in your calculator. Okay, once we've got it all plugged in, it's going to be 90 times, oops, I hit the wrong button. Not any better. There we go. E to the 0.05 times 30. And I have 403. So the amount I have after 30 days is 403 point, did I say how to measure? No. Or how to round. I'll just say 0.4 grams after 30 days. Okay? That's it. So just plug in the number, plug it in your calculator, and then simplify. Okay, the last one here is a decay problem. So this is growth. This bacteria is growing. You're going to see in the directions it talks about uninhibited growth. What we're saying is, if I've got some bacteria in like a petri dish, then it's going to be inhibited by how big the dish is. So as this stuff grows and grows and starts to fill up the dish, then the rate may slow down. So we're not accounting for that. This is just very basic, simple. If you want to go take some college level biology class, then you may kind of factor in how the growth rate could change over time. If you've got a population of animals, their growth rate is going to be determined by things like drought, the number of animals, like their prey. If that dwindles down, then their numbers may dwindle down as well. So right now we're just saying this is basic. We're not inhibiting ourselves with anything. So that's why you'll see this uninhibited growth when you're looking at a lot of problems. Okay? Now, radioactive decay. You've got this radioactive material. It's called strontium-90. It's a radioactive material that decays according to this function. So here's our function, where AO, so this little subscript, that usually means the initial amount. Okay, and you'll see that in science a lot. You'll see V with a little O. That means the initial velocity of something. Okay, so that's your initial amount. A is the amount present at time t. If a scientist has a sample of 100 grams of strontium-90, how much will be left after 28 years? So here is my formula. I want to know how much I'm going to have in 28 years. I'm starting with 100 grams. That's my initial amount. All right, my time ran out on my video. All right, I plugged in at 28. That's my time. 100 grams, that's what I'm starting with. So 100 e to the, there's my negative 0.0244. That's in this case, this is called a decay rate. And that's how fast this stuff is decaying over time. And then times 28, because that's my time. Okay, so plug all that in your calculator. Hit equals. And you should get about 50.5 when you round. Okay, so we started with 100 grams of this stuff, and now we have almost exactly half the amount that we started with. We started with 100, now we've got almost 50. So a lot of times when you're talking about things decaying, you hear of something called a half-life, and that's literally the amount of time that it takes this stuff to decay to be exactly half of what it was before. So in 28 years, this stuff goes from 100 grams down to 50. If you did another 28 years, it would go from 50 down to about 25. Okay, it wouldn't be gone. Okay, it just keeps going by half, by half, by half. Another 28 years after that, you're going to have like 12.5. Okay, so that's something that I will mention later on. We're going to solve some equations that involve these, but for right now, this is all you need to know. Okay, just how to plug it into your calculator, simplify it, and get an answer. All right, thanks.